This is section 9.3b, geometric sequences and series. A finite geometric series is the nth partial sum of a geometric sequence. Okay, so here it helps to recall what we did with arithmetic sequences. Just as an arithmetic sequence, if you call the sum of that, if it's a partial sum, it's called a finite arithmetic series. And if it's an infinite sum, it would be an infinite arithmetic series or simply an arithmetic series. Well, the same is true of geometric sequences and series. So a series is just a sum. A series is a sum. And when we're talking about an nth partial sum, we're talking about a finite geometric series. Okay, and that's written in the following way. S sub n, notice this is the same symbolism that we used for arithmetic sequences and series. S sub n, meaning the nth partial sum, equals, and we have our sigma notation, lower limit, upper limit, I equals 1 to n, of a sub 1 times r to the I minus 1. And we've already talked about, the sigma notation. We've talked also about geometric sequences. So the way that this is defined should be nothing new. A sub 1, the first term, times the common ratio raised to the I minus 1 power. And of course, the variable name doesn't matter, whether it's I, N, J, K, doesn't matter. The form is what matters. So the nth partial sum of a geometric sequence is written with these symbols. And that equals, now this is something you should write down. This is a formula that we're going to derive. But you should write this formula down because it's going to save you a lot of time. Just like Gauss's formula for nth partial sums of arithmetic sequences saved you time. In the same way, this formula is going to save you time for nth partial sums of geometric sequences. Okay, let's see how this works. So the best way, I think, to derive this formula is to do it the long way, kind of like we did before when we were, trying to derive Gauss's formula for arithmetic sequences and series. Well, in the same way, we're going to try to go through this the hard way, and that should do two things. First, it'll show you how how the formula works and where it comes from. But second, it'll show you why it's valuable to learn the formula, because it saves you time. All right, so let's look at this example. This example is the 12th partial sum, of the geometric sequence, 4 times 0.3 to the I minus 1 power. 4 being our a sub 1, 0.3 being our common ratio, r, and I minus 1. So this 12th partial sum is the same as, or is an example of, a finite geometric series. A finite geometric series. Now, again, to clarify, I know that series sounds like a bunch of things. The World Series, best of 7 games. We're used to thinking of series as a bunch of things. That's sometimes a source of confusion. But you can't go wrong if you just remember in math, a series is a sum. A series is a sum. All right, so we have our S sub 12, 12th partial sum, sigma notation. And what I'd like you to do now is do this by hand. Do this by hand. What that means is you've got different i's here from 1 to 12. I want you to plug in each successive I from 1 to 12 and add up the terms, and let's see what you get. So pause the video, do that, and then resume when you have an answer. All right, well, doing it the long way, Doing it the long way looks like this. This is our geometric sequence, and we simply fill in for I the values 1 to 12. So when I equals 1, 1 minus 1 is 0, and anything raised to the 0 power is 1, so 4 times 1 is 4. And then we do our next term, 4 times 0.3 to the 1, because since this is our second term, where I equals 2, 2 minus 1 is 1, therefore 1 is here. And so on. Third term, 3 minus 1 is 2, and so on until we get to the 12th term. And 12 minus 1 is 11, so this is raised to the 11th power. And when we add all these up, this is the answer you should get, 5.714, rounded off. Okay, so that's the long way. Now let's derive the formula. Let's derive the formula, and the formula that I'm talking about is the one there in the upper right, the nth partial sum of a geometric sequence is a sub 1 times 1 minus r to the n in the numerator over 1 minus r in the denominator. And this is the formula that we're trying to derive. And it's interesting, remember when we derived Gauss's formula for arithmetic series? Well, we kind of had to put two different sums together and recognize the pattern. We're going to do something similar to that here. Okay, so if we write out an S sub n, an nth partial sum, in general form, it looks like this. It's just a sub 1 plus a sub 1r plus a sub 1r squared. And it helps, I think, as I'm showing you what this looks like in general. Notice where the cursor is, S sub n. All this is talking in general. Where does that come from? Well, let's look back at the specifics of this example. Notice it follows the same pattern, because this is just a sub 1 times r to the 0 power, and since that's 1, this term here is just a sub 1, just like in general it's a sub 1. Over here I have a sub 1 times the common ratio to the 1 power, and that just gives me a sub 1r, and a sub 1r is my second term in general. So you can see that all I've done here is written in general terms the same exact pattern that we already saw up here. And notice that just as this 11 is my I minus 1 from the specific case, because 12 minus 1 is 11, well, in the general case, notice that this last exponent is n minus 1. Again, it doesn't matter whether we're talking about i's or n's or k's or j's. All that matters is that there's a variable. And this general form fits the pattern in which the last exponent, and I'm talking about the exponent of the very last term, equals the number of terms in the nth partial sum minus 1. Okay, so this first line is simply writing out the nth partial sum the long way, and it's doing it keeping things in general terms as variables rather than filling in specific numbers. Okay, now let's get to the actual derivation. Well, the reason I wrote it this way, I could have written the equal signs under each other, as we often do with different when there are several equations in a system or in a row. We just often line up the equal signs. But the reason I didn't here is because I wanted to emphasize a certain pattern that shows up. Okay, so this is just r, the common ratio, times S sub n. And the first line is simply S sub n. So the difference between the first line and the second is that in the second we have r times S sub n. And if I do r times S sub n, well, using, keeping in mind the distributive property, that's the same as multiplying each term of S sub n by r. And so what that looks like is a sub 1 r. See how this is just a sub 1, and then the only difference is a sub 1 times r. And then this next term is a sub 1 r, but notice that if I times that second term by r, I get a sub 1 r squared. And then this third term of S sub n is a sub 1 r squared. And this term here, which is the third term of r times S sub n, that's just the dot dot dots. But all that would be is a sub 1 r squared times r, which is a sub 1 r cubed. All right, so I can see that the only difference between the first line, which is S sub n, and the second line, which is r times S sub n, is that each term in the second line is multiplied by an extra r. And so what we end up with is two lines that look very much the same, and the only thing they differ in is the first term of this first line and the last term of the second line. And if we subtract the second equation r times S sub n, if we subtract the second equation from the first, and the first equation is S sub n equals etc., etc., etc. If we do that subtraction, this is what we get. We have on the left side S sub n minus r times S sub n. And notice that, just follow the arrow there, S sub n minus r times S sub n, because we're subtracting the second equation from the first. So this would be the left side of the new equation, S sub n minus r S sub n. And then the right side is just everything here on the first line minus everything here on the second line. And as we can see, because of the way we line things up, these a1r cancel, and then these a1r squareds cancel, and then these a1 r to the n minus 2's cancel, etc. And so all we're left with is a sub 1 minus a sub 1 r to the n. Alright, and now just using algebra 1 techniques, we can see how this simplifies. This simplifies because the S sub n comes out, factor it out. We also can factor out the a sub 1. And we're left with S sub n equals a sub 1 times the quantity 1 minus r to the n over 1 minus r. And if I plug these numbers in, okay, I'm going back up now to the specific example, the specific geometric sequence 4 times 0.3 to the I minus 1. If I plug that in, if I plug these specifics in to a sub 1, that would be 4 here, and then 1 minus r to the n, of course, is the same as I, and that's just 12 over 1 minus r. That ends up being 5.714. And as you can see, it's a lot easier to do that than to chug and plug 12 different terms. So we've now derived the formula above, and that formula above in the upper right portion of the screen is a sub 1 times 1 minus r to the n over 1 minus r. Now, I like to, when possible, derive formulas, and I've explained why before, why I like to do that. But the good news for you, I suppose, is that I don't usually ask for derivations on tests. When we get to trig, I will do that once or twice. But for now, the thing you need to write down is this formula in the upper right. You're going to use it a lot. It's going to save you time. If there is anything about the derivation that you didn't quite follow, don't worry about it. Okay, don't worry about it. All right, let's look at another example. Find the eighth partial sum of the sequence below. Okay, this is our sequence. So what I'd like you to do is put on your thinking caps. I don't know if they even say that anymore. I remember when I was in 4th and 5th grade, teachers would sometimes say, put on your thinking caps. So, you know, maybe that's something they don't say anymore, but I think you know what I mean. Put on your thinking caps and try to figure this out on your own. Press pause and resume, and then, you know, of course, don't get stuck on it too long if you can't get an answer. And so resume when you get stuck or have an answer. All right, so let me walk you through the solution now that you've tried to do it on your own. So we're asked to find the eighth partial sum. Then we're only going to be looking at the first 8 terms. Okay, that's what a partial sum is, of course. It's not the full sum. It's just a partial sum of a certain number of terms. So our n is 8, number of terms is 8, and our a sub 1 is 5. That's obvious. This is the first term. And our common ratio is 2. Now, how do we get 2? Well, 10 divided by 5 is 2, 20 divided by 10 is 2, 40 divided by 20 is 2, 80 divided by 40 is 2, etc. Alright, so that's our common ratio. Then we know we're definitely dealing with a geometric sequence. And just to quickly review, I know that the example didn't ask you to find the formula for the nth term, but repetition is the mother of learning, right? Repetitio mater studiorum. So the more we repeat things, the higher the probability that at least some of what we repeat is going to be engraved in your minds. Alright, so the formula for the nth term of this sequence is a sub n equals a sub 1 r to the n minus 1 equals 5 times 2 to the n minus 1. And this is really just a review of the last section. This is the common form of the nth term of any geometric sequence. So this is just a review. And so all we do is we fill in our givens, things that we found. 5 times 2 to the n minus 1. This is a specific geometric sequence. And I'm asked to find the eighth partial sum of it. How do we do that? Well, you could do it the long way, going through the steps 8 times, or you could use the formula that we just arrived on the last screen, and that's the best way to go. So the eighth partial sum is using the formula we learned. S sub n equals a sub 1, 1 minus r to the n over 1 minus r. Then we fill in our givens. That's 5 times 1 minus 2 to the 8 over 1 minus 2. And then we calculate through all that, several steps, and we finally end up with 1,275. And that is the eighth partial sum of the geometric sequence 5 times 2 to the n minus 1. So review terms. This 1275, this is a finite geometric series. Now it doesn't look like a series. It's not a bunch of things. It's a sum. A series is a sum is a series is a sum, all right? So this that I'm circling now with the cursor, with the arrow, this is a finite geometric series, also known as an nth partial sum. In this case, it's the eighth partial sum of this that I'm circling now with the arrow, this geometric sequence. All right, now we're going to talk about infinite geometric series, and the sum of all the terms of a geometric sequence is called an infinite geometric series, or simply geometric series. So when you see geometric series and you ask yourself, well, is it finite or infinite? If there's no adjective before geometric, you know that you can assume that it's infinite. Infinite. All right, so how does this work? Well, remember how when we were doing, when we first introduced sequences, and like there were cases where even though there were an infinite number of terms, the series approached a finite number. Well, that's what we're going to see here. The conditions are the following. If the absolute value of r, remember that r is the common ratio, if the absolute value of r is greater than or equal to 1. Okay, so if r is 2, then the absolute value is greater than or equal to 1. If r is negative 3/2, then the absolute value is greater than or equal to 1. Okay, if this is true, then the infinite geometric series, or simply called the geometric series, then the infinite geometric series has no sum. All right, why is that the case? Well, let's kind of examine why that's the case. For this specific infinite geometric series, and notice that this specific example I'm giving you here matches exactly the specific example from the last screen. All right, we're talking about the same geometric sequence. 5 times 2 to the I minus 1 power. All right, but notice now that the upper limit is infinity. And so therefore, this is not a partial sum. This is simply a sum. This is called a geometric series, or an infinite geometric series, as opposed to an nth partial sum or a finite geometric series. All right, so this is what it looks like written out. Notice that there's no subscript for the s. It's just s. And notice that the upper limit is infinity. All right, well, if I look at this common ratio 2, well, the absolute value of 2 is greater than or equal to 1. Well, what happens? As I keep plugging in bigger and bigger values of I, I'm going to start getting really huge numbers. And if I just keep adding huge numbers to a sum, well, there's going to be no limit, and therefore this increases without bound. All right, you'll see this terminology sometimes in pre-calculus and calculus. To increase without bound means it just gets bigger and bigger, never stops, and therefore there is no sum, because you can't write the sum as a finite number. You can't write the sum as a finite number, and therefore we say that there is no sum. This should illustrate why, when r is greater than or equal to 1, the particular geometric series increases without bound. Now, what happens if the absolute value of r, the common ratio, is less than 1? If the absolute value of r is less than 1, then the geometric series, which is here written in general terms, a sub 1 plus a sub 1r plus a sub 1r squared plus a sub 1r cubed, etc., has the sum s equals I equals 1 to the infinity, or 1 to infinity, a sub 1r to the I minus 1, and that equals a sub 1 over 1 minus r. Okay, now you might be saying, whoa, where did that come from? All right, we're going to get to that. But first, again, repetition's the mother of learning. Let's go through each of these step by step. Why do I write s with no subscript? Because I'm talking about a geometric series, also known as an infinite geometric series, and I don't write s subscript infinity. All right, notice that my upper limit in sigma notation is infinity, so from 1 to infinity. And this is simply the general way that we've been writing geometric sequences all along. A sub 1 times r to the I minus 1. That equals a sub 1 over 1 minus r. Notice that this formula is even simpler than the nth partial sum formula that we did on the previous screens. So definitely write this formula down now before we go into the derivation on the next screen. When you're dealing with an infinite geometric series, you can use this formula as long as absolute value of r is less than 1. If the absolute value of r is greater than or equal to 1, then the series simply increases without bound, and there is no sum. All right, so why is this true for common ratios whose absolute value is less than 1? Well, we've already proven that s sub n, we're talking about nth partial sums here, and this is just something we've already proven on previous screens. S sub n equals sigma I equals 1 to n a sub 1r to the I minus 1 power, and that equals a sub 1 times 1 minus r to the n over 1 minus r. This is what we've derived. This is what we've derived. Okay, so we know that this is true. Well, let's suppose, just for the sake of deriving this, that that we plug in infinity. So if I plug n equals infinity into the formula, just supposing we could do that, right? What would I get? Well, I get something that looks like this. S sub n, n being infinity, equals a sub 1 times 1 minus r to the infinity power over 1 minus r. Well, let's pretend for a minute that this infinity is some kind of incredibly large number, 60 gazillion, or if you like, just, 300 billion. If this is a very large number, and if I know that r is fractional, because recall that all we're trying to prove is the formula when the common ratio is less than 1. So if this r is less than 1, well, and I keep raising it to bigger and bigger powers, then this r to the big exponent is going to approach 0. It's going to approach 0. Think of, let's throw out our random r, 1/2. 1/2, all right, that's less than 1. Well, what's 1/2 to the 10th power? That's 1/2 to the 10th. Tiny number. What's 1/2 to the millionth power? That's 1/2 to the millionth. That's an extremely small number. All right, so 1 minus an extremely small number, almost an insignificant number, is basically the same as 1. Okay, now I know that it's not exactly the same, but what we're talking about is something you're going to see in calculus, is a number that it approaches, As n gets very large, and as n approaches infinity, r, the small r, the fractional r, raised to that large exponent approaches 0, and therefore this 1 minus r to the infinity starts to look really just like 1. All right, and so this a sub 1 times 1 minus r to the infinity becomes a sub 1 times 1. 1 minus r doesn't change. And that, of course, is the same as a sub 1 over 1 minus r, which we set out to prove. Again, if for some reason you're a little fuzzy on the derivation, don't worry about it. If you're curious, you can ask me in class, we can go through it. But the main thing is, write this formula down. Okay, write this formula down. I've tried to show you where it comes from. It makes sense. If you still have a question, ask me later. Write this formula down, though. What this formula is for, once more, I'll repeat it. This is the formula for finding a geometric series, also called an infinite geometric series, when there is an infinity of terms. But this formula only works when r, the absolute value of r, is less than 1. If the absolute value of r is greater than or equal to 1, then this formula will not apply at all, because you simply cannot find a geometric series for common ratios that are greater than or equal to 1. They increase without bound. All right, so you should be able to do this problem on your own. Actually, I kind of got you started on it a little bit. But you're going to find the sum of 3 minus 1 plus 1/3 minus 1/9 plus, and so on. When you see the dot 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 at the end, you know, even though they don't explicitly tell you, you know that they are talking about an infinite geometric sequence. And if you find the sum, well, then you're trying to find the infinite geometric series, or simply the geometric series. So here you have to find the geometric series, the sum of all this infinity of terms. So pause the video, do this on your own, and then resume when you have an answer. All right, some of you who are fast probably saw those things that slipped out in the last, before I went through it, and that is the common ratio we can get simply by looking at successive terms. And negative 1 divided by 3 is negative 1/3. 1/3 divided by negative 1 is negative 1/3. Negative 1/9 divided by 1/3 is negative 1/3, etc. So that's our common ratio. We can see now that r, this negative 1/3, its absolute value is less than 1. Therefore, this formula applies. And then all we have to do at that point, once we've determined that we can use the formula and that the sum doesn't increase without bound, it's just a matter of chugging and plugging. 3 over 1 minus negative 1/3. Then just keep doing the math, and you end up with 9/4. So the sum, or series, of this sequence is 9/4. remember that a sum is a series, and if there's no adjective before series, you can assume that it's an infinite series. So the sum or series of this particular sequence, this geometric sequence, is 9/4. Here's the classwork. Page 670. Please write these numbers down, and we'll see you in class.